Welcome you all for GATE coaching classes sponsored by AICT Prerana. I am Shivakumara MJ, faculty in the Department of Civil Engineering CMRIT. So in our previous session, we were discussing about engineering mechanics under section 2, that is structural engineering. So in today's session, we will discuss about solid mechanics, nothing but strength of materials. So under that, a few topics, that is bending moment and shear force in statically determinate waves, and then simple stress and strain relationships and some problems under the same. Simple bending theory. So under that, flexural and shear stresses we are going to determine. Shear center, uniform torsion, transformation of stress, buckling of column, combined and direct bending stresses. So this is what the syllabus according to GATE 2021, if you see. So in this, I will start with simple stress and strain relationships. So in your strength of material, that is a third semester subject, you have already studied. Some introduction part I will start with. So simple stresses and strain. Before applying the concept of stress and strain, let us try to understand the definition of stress, strain, and how to use the mathematical relationship under the same. So stress basically the force of resistance per unit area offered by the body against the deformation. So whenever you apply a certain force, that is an external force or the load acting on the body, normally the body will try to deform under the application of force. So against this deformation, the material will offer the resistance. So this resistance, if we account per unit area, so that is nothing but stress. So basically it is a resistance force. Okay, that intensity we are going to calculate. So that is why per unit area we are going to calculate. Normally a loaded member remains in equilibrium when the resistance offered by the member against the deformation and the applied loads are equal. If the material is not having the enough strength, or if the material won't offer the resistance equal to the applied load, the body will not be under equilibrium. If it offers and applied load equal to resistance offered by the material, then the body is under equilibrium. And the mathematical relationship for the same, it is sigma notation we are going to use for stress. So sigma equal to applied load divided by cross-sectional area. So P is the externally applied force or the load, and A is the cross-sectional area. So unit of force, that is kilonewton, Newton, whatever. And then a unit of area, that is meter square, mm square, centimeter square, whatever it can be. So finally, the unit of stress is Newton per mm square. You can also use convenient way of unit of stress. It can be kilonewton per meter square, Newton per meter square, Newton per mm square, whatever, that's fine. And then next topic, it is strain. So when the body is subjected to some external force, there is some change in dimension normally. Okay, when there is a change in dimension of the body, so under such situation, if you take the ratio of change of dimension of the body to original dimension, okay, normally the material will experience a certain deformation. So you will measure that deformation, so how much it is. So with respect to original dimension, we compare. So the ratio of change in dimension to the original dimension is known as strain. There are different types of strain the material will experience. So it can be tensile strain, compressive strain, volumetric strain, and shear strain. So if there is some increase in length of the body due to application of external force, then the ratio of increase in length to the original length of the body is known as tensile strain. Okay, if there is an increase in length, okay, that you will have to look after. But if there is any decrease in length of the body due to application of force, the ratio of decrease in length of the body to the original length of the body is known as compressive strain. So reduction of size, compressive; increase in size, tensile. The ratio of change in volume of the body to the original volume is known as volumetric strain, and then the strain produced by the shear stress is known as shear strain. Totally four types of strain we are looking after here: tensile strain, compressive strain, volumetric strain, and shear strain. And then types of stresses. Normally, two main types of stresses are there. That is normal stress and shear stress. So normal stress is a stress which acts in the direction that is perpendicular to the cross-sectional area. So it is represented by sigma. Already I showed that. And then normal stress is further divided into tensile stress and compressive stress. So tensile stress, the stress induced in a body when it is subjected to two equal and opposite pulls. Okay, we are pulling the object from both the sides with the same magnitude of force, as a result of which there is increase in length of the body. So this type of stress is known as tensile stress. The ratio of increase in length to the original length is known as tensile strain. Already I have seen this tensile strain. So tensile stress acts normal to the area and it pulls on the. And the next it is compressive stress. So compressive stress here, what will happen? The stress induced in a body when it is subjected to equal and opposite pushes. Over there, in case of tensile stresses, it was pulling the object. Over here, it is pushing the object from both the sides. Over here, obviously, due to push from both the sides, there will be decrease in length of the body. So such type of stresses known as compressive. The ratio of decrease in length to the original length of the body is known as compressive. And then mathematical relationship, tensile stress sigma equal to resisting force divided by cross-sectional area. So that resisting force is nothing but it will be equal to tensile, so that is P by A. And then tensile strain equal to change in length or increase in length, that is TL, and the original length L. It is the ratio of change in length to the original. So if you apply the force in this direction, resisting force will be opposite in nature, which will be acting in direction. So in the same manner, compressive stress also is a resisting force, that is pushing force divided by cross-sectional area, and then compressive strain will be change in length by original. And then shear stress, so basically it is tangential in nature, which will act at the surface of two bodies. The stress induced in a body when subjected to equal and opposite forces, which are acting tangentially across the resistance section. So you can see these sketches, as a result of which body will tend to shear up across the section. So such type of stress is known as shear stress. The corresponding strain is known as shear stress. So shear stress is the stress which acts tangential to the area. So it will be represented by tau. Shear stress, we are going to represent it by tau. And the normal stress, we are representing by sigma. This is the formula: shear stress equal to shear resistance divided by shear. And then next topic is modulus of elasticity. You can call it as Young's modulus also. Basically, it is the ratio of stress to strain. The stress to strain relationship, it can be tensile or compressive in nature. The ratio of tensile stress to tensile strain is constant. Okay, it is proposed by Young's, that is why it is Young's modulus, we call it as. So E equal to, stress is directly proportional to strain, whatever we say, where that proportionality limit we call it as Young's modulus or modulus of elasticity. And then finally we arrive at Young's modulus of elasticity. Young's modulus equal to E equal to sigma by E, stress to strain. So that should be within elastic limit. And then next one, it is modulus of rigidity or shear modulus. The ratio of shear stress to the corresponding shear strain within the elastic limit is known as modulus of rigidity, or you can also call it as shear modulus. It is denoted by G. So tau by phi shear stress to shear phi. Now factor of safety. Factor of safety is the ratio of ultimate stress to permissible stress. Okay, so ultimate stress up to which the material or the object can be stressed, upon which if you increase the material is going to fail. Permissible stress up to the limit where without any like considerable deformations you can stress the. So that is a factor of safety, and factor of safety for different material it is different. So it is based on the property of material. It depends on to fix the factor of safety for different materials we use in construction industry. And then longitudinal strain and lateral strain you need to understand. So when a body is subjected to actual tensile load, there is an increase in length of the body. But at the same time, what will happen? If you extend the body in one particular direction, there will be reduction in size in perpendicular direction. Okay, but at the same time, there is decrease in other dimensions of the body at right angles to the line of action of applied load. Thus, the body is having axial deformation also in the direction right angles to it to the line of action of applied load. So that strain we call it as lateral strain. So whatever the deformation happens in the direction of applied load in the longitudinal direction, that we call it as longitudinal strain. Whatever the deformation happens in the direction perpendicular to the direction of applied load, that is lateral strain. So the ratio of axial deformation to the original length of the body is known as longitudinal strain. The longitudinal strain is also defined as deformation of the body per unit length in the direction of applied. So diagrammatic representation you can see over here. So there is an object over here which is applied with a force P. So due to application of force P, original length was this. Because of application of force, there is increased length. So here del L is the increased length. So this increased length del L divided by L is known as longitudinal. So due to increase in length in this direction, there is a reduction in size in perpendicular direction. So that is shown in this cross section. So due to reduction in size, in breadth and depth, both the sides. So lateral strain, you can write it as del B divided by P or del D divided by P. So that is the lateral strain. You can see over here del B by B, del D by looking at that step. So two types of strain because of application of force you had seen. And then you see here, note it is very important. If a longitudinal strain is tensile in nature, then the lateral strain will be compressive. Can you see this? See this sketch? The longitudinal strain is tensile in nature. We are pulling the object from both the sides. So due to this pulling in perpendicular direction, there is reduction in size. So in this horizontal direction or longitudinal direction, the material is experiencing the tensile strain. At the same time, because of reduction of size in the perpendicular direction to the applied load, there is compressive strain the material is experiencing. Okay, so that is why the statement, if longitudinal strain is tensile in nature, the lateral strain will be compressive. And it is vice versa. If longitudinal strain is compressive in nature, then the lateral strain will be tensile. Hence, every longitudinal strain in the direction of load is accompanied by lateral strain of opposite kind. Lateral strain of the opposite in all the direction perpendicular to the direction of light. Is it clear, these 3 points? Any doubts in this? Someone of you,
No, sir.
no issues, right? Fine. Now, Poisson's ratio. It is the ratio of lateral strain to longitudinal strain. It is a constant that is represented by the ratio of lateral strain to the longitudinal strain is constant for given material. When the material is stressed in within elastic limit, okay, that you will have to see. When the material is stressed within the elastic limit, in such situation, the ratio of lateral strain to longitudinal strain is a constant. Okay, that constant is nothing but Poisson's ratio. So mu equal to lateral strain by longitudinal strain. So that lateral strain you can cross multiply it mu into longitudinal strain. Okay. So and this one also you will have to see over here. As lateral strain is opposite in sign to the longitudinal strain, algebraically you can write lateral strain equal to minus mu into longitudinal strain. So this one you need to understand over here. We have written lateral strain equal to minus mu into longitudinal strain. So normally when we write like this, when longitudinal strain is tensile in nature, we will have to show lateral strain as compressive in nature, right? Right? Hello.
Yes, sir.
When the longitudinal strain is tensile in nature, lateral strain must be compressive in nature. So tensile strain, we take it as positive. So here we are maintaining minus negative sign over here, minus mu into longitudinal strain. By this negative sign, we are showing that lateral strain is compressive in nature. Okay. If longitudinal strain is negative, then you must show lateral strain as what? Lateral strain as positive, right?
Yes, sir.
When the longitudinal strain is negative, that means what? Longitudinal strain is compressive in nature. So in such situation, lateral strain must be tensile. So this sign convention must be positive. Okay. And then the relationship between stress and strain for planar elements. So two-dimensional figure ABCD we have taken over here. Two mutually perpendicular stresses, that is the sigma 1 and sigma 2. Over here, the overall strain we are trying to calculate, that is E1 and E2. So E1 equal to sigma 1 by E minus mu into sigma 2 by E. That means sigma 1 by E, that is stress in horizontal direction. So the sigma 1 is tensile in nature for this area. So it is plus sigma 1 by E. And then due to sigma 2, due to sigma 2, there is certain compressive strain also this section is experiencing. Are you getting this point? Due to application of sigma 2 in this direction, there is certain compressive strain in this direction. Are you getting this? So that compressive strain is nothing but minus mu into sigma 2 by E. And in the same manner, E2 equal to sigma 2 by E. That is, due to application of sigma 2, there is certain longitudinal strain in this direction. And at the same time, due to application of sigma 1, there is lateral strain in this direction. So that is nothing but minus mu into sigma 1 by E. We got these two things, E1 and E2. Why we have subtracted with the minus mu sigma 2 by E and mu sigma 1 by E. You got this point? Jay Surya?
Yes, sir, understood.
Okay, how about Chandana?
Yes, sir, understood.
Okay, fine.
Yes,
So
sir.
in the same manner, this is for two dimensional, it's okay. In the same manner for three-dimensional. Okay, sigma 1, sigma 2, and sigma 3. So totally three normal stresses are acting on a cube. So in such situation, the total strain, that is epsilon 1 or E1, equal to sigma 1 by E. So sigma 1 by E, that is longitudinal in nature, minus sigma 2 mu into sigma 2 by E. So mu into sigma 2 by E, that is due to sigma 2 acting in y direction, because of which there is lateral strain in x direction. So that is mu sigma 2 divided by E minus mu sigma 3 by E. So minus mu sigma 3 by E, why? Because sigma 3 is acting in z direction. So there is a longitudinal strain in z direction due to sigma E. So perpendicular to that perpendicular direction, lateral strain, the material is experienced. So that is why it is minus sigma 3 by E into mu. In the same manner, if E2 and E3, sigma 2 by E minus mu into sigma 3 by E minus mu into sigma 1 by E. Similarly, the formulas are written. Okay, so this is what an introductory part for a simple stresses and strain. So before solving problem, if you have any doubts, you can ask. You have 1 minute of time to ask your doubts in the introduction. Stress, strain, types of stresses, modulus of elasticity, modulus of rigidity, factor of safety, Poisson's ratio, relationship between stress and strain for a two-dimensional element, and for three-dimensional elements in stress and strain relationship. Yeah, no doubts. Shall we go for solving problems?
Yes, sir.
Yeah. So first problem, question is direct. You will have to determine stress, you will have to determine strain, and you will have to determine elongation of the rod. And now you come for details of the rod. There is a rod of 150 centimeter long. Length of rod is given, original length, and its diameter is 2 centimeter. There is nothing but 20 mm, and it is subjected to an axial pull of 20 kilonewton. There is nothing but 20 into 10 raised to 3 Newton. If the modulus of elasticity of the material is 2 into 10 raised to 5 Newton per mm square, what is this modulus of elasticity means? The value of E is 2 into 10 raised to 5 Newton per mm square. You will have to determine stress, strain, elongation. Okay, the given data, L is equal to 150 centimeter, they are given. So if you convert that into mm, why we are converting into mm? So see over here, modulus of elasticity, it is given in terms of Newton per mm square. Okay, or either you will have to change this unit from centimeter to mm, or if you want to retain centimeter means you will have to change this to Newton per centimeter square. So that you should ensure first. So length equal to 150 mm, nothing but 1500 mm, and diameter equal to 2 centimeter, nothing but 20 mm. And then cross sectional area of this rod with respect to 20 mm, it is calculated, that is 100 pi. So you can substitute for pi also. And then axial pull, it is 20 kilonewton. It is nothing but 20 into 10 raised to 3 Newton. E value it is given. Now first question you come for stress. So which formula we should use, Harshan? For stress?
Load by area.
Load by area. What is load over here?
Load 20,000 Newton.
20,000 Newton. And then area?
100 pi.
100 pi. If we solve this, we have
63.661.
yeah 63.662
661.
equal to P by A, 20,000 divided by 100 pi, 63.662 Newton per mm square is the answer. And then stress, we are done with it. And then strain we will have to calculate. So which formula you will use, Jaisodya, for this calculation of strain?
Sir, stress by modulus, Young's modulus.
Yeah, basically relationship between stress and strain, that is Young's modulus E equal to stress by strain. So stress already we have calculated, and Young's modulus value here it is there. So E equal to stress by strain, strain equal to stress by modulus. So stress value 63.662 divided by Young's modulus 2 into 10 raised to 5 Newton per meter square. So you will get 0.00318 is the value of strain. Chandana, here they are not given the unit of measurement strain. What is the issue here? It was
Sir?
supposed to be written.
No,
It
no,
was
sir.
supposed to be written
No,
or not?
no
No,
unit,
right?
sir.
So strain, there is no unit, right?
Yes, sir.
Yeah, it is a dimensionless quantity. Yeah, good. And then third question, it is elongation of the rod. So it is just asked what is the elongation of the rod. So what is the initial length of the rod? 150 centimeter, that
150.
is 1,100 mm. So we have formula strain equal to change in length by original length. Strain we have already calculated 0.000318. If you multiply this strain with the original length, you are going to get the elongation value, that is change in length value. So how much is the change in length value? So here we have multiplied 150 centimeter, in place of which if you multiply 1500 mm, answer would come in terms of mm. So 0.0477 centimeter is the elongation. So this is the very simple problem where relationship between stress, strain, and modulus of elasticity. So next formula, I want someone to read and tell me what to be. We're all there in class.
ಅದರಲ್ಲಿ ಸ್ಟ್ರೆಸ್ ಕೊಟ್ಟಿದ್ದಾರೆ ಸರ್
Okay, fine.
ಸಿಗ್ಮಾ
Yes, Jamuna is there, Ruchita is there, Janardhan, Jackie, Devraj, Chandana. Yes. Okay, fine. Yeah, Jamuna, you can read this question once.
Yes, sir. Find the minimum diameter of a steel wire which is used to raise a load of 4,000 Newton if the stress in the rod is not exceed 95 meganewton per meter square.
Yeah. So here basically what we need to determine, we have to determine
Minimum diameter of the steel wire.
steel bar. Okay, the given data, it is noted here. The load which we have to lift is 4,000 Newton. And then the rod is not, stress in the rod is not to exceed how much? 95 meganewton per meter square. Okay. So what is mega? It is 10 raised to
6.
If you convert a meter square into mm square, what
10
if you
power,
convert
10
10
power
raised,
minus 6.
10 raised to 6, it will come in a denominator. If it comes to numerator, it will become 10 raised to minus. So 10 raised to plus 6 due to mega and 10 raised to minus 6 due to meter square to mm square gets cancelled. So that stress in the rod should not exceed how much? 95 Newton per mm square. And then diameter of the wire we need to calculate. Cross sectional area formula pi d square by 4. So stress equal to load by area. Load is 4,000 Newton. Area pi d square by 4. So 4 will go up. 4,000 into 4 divided by pi d square, which is equated to 95, where the stress should not exceed this limit. So by cross multiplication, so d square you will get 53.61. To take a root of it, you will get 7.32 mm. So minimum diameter of the bar should be 7.32 mm must be there, so that we can lift 4,000. So by applying a certain factor of safety, you can go for increasing the diameter also. But however, the minimum diameter requirement is 7.32. And then next problem, under stress strain relationships. The safe stress of a hollow steel column, which carries an axial load of 2.1 into 10 to 3 kilonewton, is 125 meganewton per meter square. Okay, safe stress already there. If the external diameter of the column is 30 centimeter, determine the internal diameter of the column. So internal diameter of the column, if you determine the thickness of that hollow section, basically we can. So safe stress 125 meganewton per meter square, which will be equal to 125 Newton per mm square. And then axial load 2.1 into 10 raised to 3 kilonewton they have said. So that if you multiply with 10 raised to 3 again, you get 2.1 into 10 raised to 6 Newton. And then diameter, it is external diameter given, that is 30 centimeter, nothing but 0.3 meter. Here we have converted everything to meters. So in meter only you should maintain all the dimension. And then small d is the internal diameter. So the cross section of the column, only the material where exactly it is there means. So external dimension minus external dimension cross sectional area minus internal dimension cross sectional area. If you do, you will get an exact cross section where the material is there. So this is the formula A equal to pi into capital D square minus small d square divided by 4. So small d we do not know. Sigma equal to P by A. We have sigma value. We have P value. Only the thing is in A we do not know D. Substitute the sigma. You are going to get 26.19 centimeter as the internal diameter. Okay. You can see the calculation. P square is equal to 0.09 minus 0.02139. So by looking at this, I want Ruchita to tell what is the thickness of this hollow section. So we determined over here internal dimension as 26.1. So external dimension already it was given in the problem statement itself. So what's the thickness of this hollow section, Ruchita? Ruchita, are you there? Devraj?
Yes, sir. Yes.
Ruchita, Hedama. Thickness of that hollow section, how much it is?
26 point.
26 point.
So you're asking the
Thickness.
what is the
Thickness of the
20
hollow section. There is a pipe, right? Internal
yes.
external diameter, it's a pipe. Hollow section, it is that hollow section. We calculated internal diameter of the hollow section. So what is the thickness of this hollow section? You can see this data in the problem statement which is given.
Yes, sir.
You can see the value of a D which is calculated here.
Yes, sir.
Yeah, what is the thickness of hollow section?
Tamam.
Jamuna?
Sir, capital D minus small d. That is 30 minus 26.19.
That's it, right? It will come around a 3.81.
3.81.
That's it.
2.81.
So external diameter, that is 30 mm, 30 centimeter, and then internal diameter, it is 26.19. See, it is not mandatory that the question should be asked in this manner only. They may ask you to calculate the thickness, right?
Yes, sir.
So if they ask you to calculate the thickness, how you will calculate? So internal diameter and external diameter you will calculate. Reduction of both, you will get thickness. So that may be 3.81. So see a problem in multiple directions. So it is not meant that in a manner where we solve the problem should be asked. No. So in the same manner, another problem, the answer is 140.85. You can take the screenshot of it and you can work out after this session. The ultimate stress for a hollow steel column which carries an axial load of 1.9 meganewton is 480 Newton per mm square. Ultimate stress here they are given. If the external diameter is 200 mm, determine the internal diameter and take the factor of safety as 4. Okay. So factor of safety, ultimate stress and permissible stress relationship, you know. And then a stress strain relationships, you know. So by using that information, you calculate. The answer is internal diameter is 140.85. You can work it out. So those are all the simple concepts and problems. Now you come for another type. So bars of varying section. So not mandatory that there should be one single bar of same dimension all the time. Based on requirements, there may be bars of different dimensions which are connected to each other. So in this, there are 3 sections of bars, section 1, 2, 3. Section 1 is area 1, area 2, area 3, different section. And length of each section also it is different, L1, L2, L3. When all these 3 bars are subjected to same magnitude of force P, which is tensile in nature, you can see over here, then stress in each section. So what type of stress all the sections are subjected to here? What type of stress?
Tensile.
Tensile stress. So all 3 sections are subjected to tensile stresses. So tensile stress in area 1, that is section 1 is sigma 1 equal to P divided by A1. So that is a load applied divided by cross-sectional area at location or section 1. In the same manner for sigma 2 and sigma 3, P by A2, P by A3. So by using this concept and at the same time, strain in each individual sections also it is different. So strain E equal to P by A1 into E. How we will get E1 equal to P by AE? You know that E equal to sigma by E. Then E will become sigma by E. So E equal to sigma by E is in place of sigma, if you substitute P by A, you will get E equal to P by A. So F E1, E2, E3. For different sections, different strain values. So total strain value, if you want to calculate, you should add all these strains individually. One simple problem. There is an actual pull of 35,000 Newton is acting on bar. So this bar is consisting of 3 lengths as shown in figure. And the material is same. So Young's modulus is 2.1 into 10 raised to 5 Newton per mm square. So here you will have to determine a stress in each section and the total extension. So stress in each section means you will calculate sigma 1, sigma 2, sigma 3. And then total strain, total extension of the bar means you will calculate DL1, DL2, DL. Okay. So what is the stress value? I want one of you to answer in section 1. Do the calculation. Load by area is the formula for stress in particular section. Here the diameter is 2 centimeters.
17.82 Newton per mm square.
Who is answering? You tell your name and tell the answer.
Jaisuri.
Okay. 17 point something. Yeah, Jamuna. Section 2. What is the stress value?
So calculating, sir.
Yeah. Suchita, what is the stress value in section 3? Devraj?
49.
Yes, I'll tell.
Section 2 ಗೆ.
Devraj?
Sir, for section 2,
Yeah. Section 2 is
sir,
Nini ಎಷ್ಟು ಬಂತು ಹೇಳಮ್ಮ ಫ್ರಾಂಕ್ ಆಗಿ. Here it is showing 49.514. How much you got?
is same, sir, 49.51.
Yeah, section 1. One was saying 17 point something. So here it is showing 111.408 Newton per meter square. Can you check once again?
Sir, I'll diameter first section one second ತೋರಿಸಿ sir.
Diameter for section 1, it is 2 centimeter.
ಅದೇ ಸರ್ 111.40.
Yeah, 111.408 Newton per mm square is the stress in section 1. So stress in section 2, 49.51. And I think section 3 answer someone had told 17.825 Newton per mm square. See the cross checking over here. You see, as the diameter is increasing, the stress is decreasing. As the diameter is decreasing, stress is increasing. It is the effect of cross-sectional area basically. Okay, that is the check. And then for total extension, you have strain, that is P by AE is the strain value. So for P by AE, if you multiply the original length, you are going to get change in length. You know formula, E equal to DL by L. So DL equal to E into L. E is P by AE. You are multiplying.
ಸರ್ ಅಲ್ಲಿ 200 ಆಯ್ತು ಸರ್ ಹಾಕೊಂಡಿರೋದು 20 ಅಲ್ವಾ ಸರ್ ಕೊಟ್ಟಿರೋದು ಸೆಂಟಿಮೀಟರ್
ಏನಪ್ಪ
L1
here they have calculated in terms of mm at the end. You see,
sir. Okay sir.
your answer is in terms of mm. You can also calculate in terms of meter also. Make sure that all dimensions are in meters. So P value 35,000 Newton, E value 2.1 into 10 raised to 5 Newton per mm square. L1 into L3. Let us see over here. L1 is 20 centimeters, nothing but 200 mm. And then 25 centimeter, 22 centimeter, 250 and 220. And then cross-sectional area, accordingly it is written. So 0.183 is the total extension experienced by these varying sections. So this is how to calculate.
Yes sir.
And sometimes for a specific member, they may ask you to calculate the extension. So calculate the extension experienced at section 2. And there may be answer options are given in MCQs like total extension value, extension at section 1, extension at section 2, extension at section 3. Okay, you have to be very careful while reading the question. So if they have mentioned section 2 means only for section 2 you will have to calculate and check. So now I want Devraj to tell what is the extension experienced by section 2 here. Extension. Devraj, why are you not responding? You are there? Idhar no?
ಇಲ್ಲ ಸರ್.
Shari?
Yes sir.
Section 2 ಅಲ್ಲಿ ಎಷ್ಟಾಯ್ತಪ್ಪ?
ಯಾವ್ದು ಸರ್?
Section 2.
ಒಂದು ನಿಮಿಷ ಸರ್.
How much is the extension experienced by section 2?
Sir, can I?
Yeah, you also can go ahead.
0.0564.
0.05?
64.
Yeah, how did you calculate?
Sir, same sir. P by E into L2 by A2.
That's it. So 35,000 into 250 divided by 2.1 into 10 raised to 5 into 225 into 5. If you do so, you are going to get extension experienced by section. Have you also got the same?
Yes sir.
Yeah, good. Yeah, now you come for principle of a superposition. So when a number of loads are acting on the body, the resulting strain according to principle of superposition will be the algebraic sum of strains caused by individual loads. So you will have to calculate the strains caused by individual loads, and then algebraic sum you will have to take. So while using this principle for an elastic body, which is subjected to a number of direct forces like tensile and compressive at different sections, along the length of the body, first the free body diagram of individual section should be drawn. Then the deformation of each section is obtained. The total deformation of the body will be then equal to algebraic sum of a deformation of the individual section. Okay, so while solving problems by using principle of superposition, you will have to calculate the strains for individual forces, and then you should take the algebraic. So one simple problem by using the principle of superposition. There is a brass bar having a cross-sectional area of 1000 mm square, which is subjected to axial forces shown in figure. See over here, it is a 50 kilonewton in this direction, 80 and 20. Actually, this 10 kilonewton, it is by mistake wrong in the direction which is shown here. It should be towards left. Okay, you consider this 10 kilonewton towards left. Okay, so here we have to find the total elongation of the bar and take E value as 1.05 into 10 Newton. Total elongation, that is total elongation. Just now we solved the problem over here. In the same manner, over here also, three sections are there: AB, BC, CD. So three sections are there. We'll have to calculate extension in each section. So based on nature of extension or strain which is experienced, whether it is tensile or compressive strain. So based on that, we should use the sign convention. We should take the algebraics. So see here, first one, 50 kilonewton. The free body diagram we are trying to write. 50 kilonewton towards left, and here 80 is there. To maintain the equilibrium, 50 kilonewton is sufficient. So 80 minus 50, remaining is 30. So that 30 will be acting on section BC. So first 50 kilonewton among this 80 is balanced by this 50, so that it became a tensile force on section AB. So remaining 30 is on BC. So in that BC, remaining 30, so 20 is balanced by this 20. Okay, so that BC, section BC is subjected to compressive force. And remaining 10 in this 30 is applied to this CD, and then this 10 is towards left. So CD section also is subjected to compressive and compressive force. So that is what it is written over here. AB 50 tensile, BC 20 compressive, and then here we are taking B to D. Overall section we are taking as the remaining 10 kilonewton is experiencing from here. So that is for BD 10 kilonewton. Okay. So if you calculate the extension of AB, what should be the sign convention? What is the sign convention?
Positive.
This should be positive. What is the sign
Positive
convention of BC and BD? It is minus. So while calculating the total extension, this should be positive, this should be negative, this should be negative. So let us see how to calculate the extension of each section. You know the formula for extension, that is PL by AE. So here for section AB, 50 kilonewton is the force acting. So in terms of Newton, if you write 15 to 10 raised to 3, divided by cross-sectional area A, that is 1000 mm square, it is given. Value of E 1.05 into 10 raised to 5, it is given. And the length of section AB, so how much it is? 600 mm.
600
mm. You substitute over here. So that extension of part AB is 0.2857. Okay. So part BC you come for P2 and L2. So P2 is how much? 20 kilonewton. That means 20 into 10 raised to 3 Newton. And then L2 is 1 meter. So it is 1000 mm. Divided by cross-sectional area, it is the same. And Young's modulus also, it is the same. So here decrease in length is happening, so that you can use negative sign for this, minus 0.005 1904. In the same manner for part BD also 10 kilonewton, so that 10 into 10 raised to 3 Newton. Then 1000 and 1.05 it is the same, but the length you see over here is 1 plus 1.2 meter from B to D. So that is 2200 mm will have to. So this equal to it is written, actually it is not equal to, multiply. Okay, multiply sign must be there. So the total extension, that is minus 0.2095. So total elongation of the bar, you can see this is positive sign first section, remaining two sections it is negative sign. So that finally it is minus 0.1142 is the answer. So minus 0.1142 means this overall bar, it is going to get compressed or elongated.
Compression, sir.
Compression. This bar is going to get compressed. Okay, by looking at that answer, we can say negative sign shows that there will be decrease in length of the bar. Then analysis of uniformly tapering circular rods. So till now, sorry, yeah.
Sir, in last problem L3, why it is taken as 1.2 plus 1?
See here for 10 kilonewton from B to D we are taking. So it is balanced from here. So 50 is towards left, 50 is towards right. So remaining is 30. So in 30, in BC section, 20 is acting in this direction, remaining 20 is acting in this direction. So there is again a remaining 10 kilonewton which is there at P.
Okay, sir.
And then actually over here what is shown 10 kilonewton towards right is wrong. The direction is wrong. It is towards actually. So this BD section is subjected to compressive 10 kilonewton force.
Okay, sir.
So come for uniformly tapering circular rods over here. So this is a derived formula. You will have to remember this 4 times of PL by pi E into D square. So in place of a D, D1 and D2, you can use. You will have to remember this formula. Total extension for determining total extension. Okay. At any particular cross section means you will have to determine the diameter at that particular section, and you will have to determine the stress at any particular section. Okay. So one simple problem, you see this formula 4 times of PL by pi into D square, or D1 into D2 you can multiply if there is huge change in diameter. 4 PL by pi E into D1 D2 in place of D square. Read this problem. There is a rod which tapers uniformly from 40 mm diameter to 20 mm diameter in a length of 400 mm. And this bar is subjected to an actual load of 5000 Newton. The modulus of elasticity is 2.1 into 10 raised to 5 Newton per square. You will have to find the extension of the rod. See, I repeat, this is a varying section where it is circular in nature. Got it? Uniformly tapering circular rod. Okay. Cross section is circular in nature. So larger diameter it is given, that is 40 mm. Smaller diameter it is given 20 mm. And length of the rod it is given 400 mm. And actual pull it is given 500 Newton. Value of E. We just substitute this formula, all these values. So DL equal to 4 times of PL by pi into D1 D2. You will get 0.01515 mm as a total extension of the bar. Okay. So do remember, one more time I repeat, you will have to remember this formula for total extension of circular tapering rod. DL equal to 4 times of PL divided by pi E into D1 D2. just like PL by AE formula you are using, no, total extension. So here PL by AE in place of PL by AE, expression for A, you know, that is area equal to pi d square by 4. So here also it is the same. Pi is there. In place of d square, we have written d1 d2. And divided by 4, that 4 is coming over here. Okay, it is easy to remember like this. PL by AE, that you know. So PL by AE, only for A you are substituting over here. Pi d square by 4, in place of pi d square by 4, you are substituting pi d1 d2 divided by 4. So 4 will go up. That's it. This is how you will have to remember. And then again uniformly tapering, but here rectangular bar. This is not circular bar, rectangular bar. So this is the derived formula for extension dl equal to PL by E into T into A minus B log of A divided by B. E is the thickness, L is the length, A and B are the width and breadth parameters. Breadth, it is not breadth, it is just depth. Breadth is constant, that is T. Okay, one problem it is given. You just need to substitute the values in this formula. You can read the question. There is a rectangular bar made of steel, 2.8 meter long, then 10 mm thickness. The rod is subjected to an actual tensile load of 40 kilonewton. The width of rod varies from 75 mm at one end to 30 mm at another end. Width of the rod. Okay. So thickness is same throughout the length. Width is varying. Find the extension of the rod if value of equal to 2 into 10 is 20. So given data, length is 2800, that is 2.8 meters is given. Length it is same throughout the length, 15 mm. And applied load, actual load is 40,000 Newton. And then the width of a bigger end, it is 75, it is given. Width of smaller end, it is 30 mm, it is given. And modulus of elasticity also it is given. So you just substitute the values, will get 0.76 mm as the total extension of a rectangular bar. Okay, varying cross section. With this formula, you will have to. Any doubts?
No, sir.
Next topic, it is bending moment and shear force in statically determinate beams. Yeah. So when do you call beams as statically determinate? Ruchita? Chandanasi? Chandanasi, when do you call beams as statically determinate beams?
Yes. So if the forces can be calculated using equilibrium equations.
Using equilibrium equations, all the unknowns in the beams you can be able to determine by using conditions of equilibrium. Okay, is that right? So some introduction for shear force and bending moment. All of you know that it will take some 5 minutes per take, and then we'll go for starting something problems. So bending moment and shear force, you can say beam as statically determinate if its reaction components or unknown reactions can be determined by using conditions of equilibrium or equations of static equilibrium. Okay. So some examples for that: cantilever beam is a statically determinate beam. Simply supported beams and overhanging beams with single span, which is extended. All those are all statically determinate beams. And there are different types of loads will act on beams. Point load or concentrated load, uniformly distributed load, uniformly varying load, and externally applied couple moments. These are all the different types of loads which will act. And you know how to convert uniformly distributed load and uniformly varying load into point load. So these beams will transfer the applied loads to the support. In the process of transmitting the applied loads, the supports the beam develop resistance to the moment and transverse shear force also. The beams will offer resistance against the applied load by transferring the load. So definition of beam, these are all the members which receives the load or load is applied in a transverse direction. And then different types of beams, horizontal, vertical, and inclined beams based on the nature, how they are kept. And there are straight and curved beams. And then statically determinate and indeterminate beams based on how we solve. And cantilever simply support fixed and overhanging beams. Statically determinate beams. These are all the equations we can use. Summation of fx equal to 0, fy equal to 0, and the summation of m equal to 0. So diagrammatic representation of cantilever simply supported overhanging, continuous, fixed end, and proper cantilever. In the pure bending case, you come for prismatic member subjected to equal and opposite couples. One fine example for the beam which is subjected to pure bending. Over here you see, so from support C 12 meter, from support D 12 meter, and 26 meter overall span in between C to D, 80 kg and 80 kg at both ends is applied. So we can say this beam is subjected to pure bending. Okay, you can also calculate the moment which is experienced by the beam. Types of loads, diagrammatic representation, UDL, UVL, point load, and then a couple moments. Different types of support, puller support, fixed support, and hinged support, and diagrammatic representation of the same. Now, shear force diagram. Shear force at a section in a beam is the force that is trying to shear off the section. Okay, it is trying to shear off the section, which is tangential in nature at the plane area. And it is obtained by algebraic sum of all the forces, including the reactions acting normal to the axis of the beam, either to the left or right of the section. Any one side you will have to consider, and you can calculate the shear force which is trying to shear off the beam. So its direction is perpendicular to the longitudinal axis of the beam. So the diagram which shows the shear force variation is SFD, bending moment diagram which shows the variation of bending moment. So sign convention which we use here for shear force, from the considered section towards left if the force is acting upwards, or from the considered section force is acting towards down, it is positive, and from the considered section towards left down means negative, towards up right side it is negative. And then bending moment, sign convention, if the moment is trying to sag the beam, it is positive. If the moment is trying to hog the beam, that is negative. One simple example for a shear force and bending moment diagram. Cantilever beam which is subjected to a point load at its free end. Okay, this is the beam AB which is subjected to point load W, magnitude of W kilonewton at point B. So this is the shear force diagram and bending moment diagram. So for point load to the support, if there is no load in between, SFDV is linear in nature. Okay, same shear force throughout the length it will experience. So shear force is positive as right side downwards with respect to left portion. So if you consider a section over here, sign convention already we saw. So load is acting towards down means we are taking it as a positive. So from here it is towards up, we should start with. So from B, we have started upwards, that is positive. And then you come, and if you calculate the support reaction, summation of Fy equal to 0 if you apply, Ra towards up and W towards down. So Ra will be equal to W. So it will come like this. So same magnitude of shear force until A. And as from the section towards left, if it is upwards negative, we said, so you should come down. Okay, this is shear force diagram. And then bending moment diagram, it is 0 at free end. As you go away from here, so for point load, W into distance. So that is W into X is the bending moment at this section. If length is L, W into L. Okay, linearly, which will vary this bending. So let us solve some problems. Shear force and bending moment diagrams. So you can note it down, this problem. So there is a beam simply supported at A and B, and some overhanging portion is there from B to C. Uniformly distributed load is acting in between the span A and E, and there is a point load 20 kN at point D and 30 kN at point C. Span remaining ED, DB, BCR 5 meters. So for drawing shear force and bending moment, the first step is to determine the support reactions. So support reactions by using conditions of equilibrium, summation of Fy equal to 0. So summation of Fy equal to 0 if you do, Ra towards up and Rb towards up positive, 20 kN towards down and 30 kN towards down negative. And then you convert this UDL into point load, that is 10 into 10, that is 100 kN is towards down. Okay. So if you do so, you will get one equation. So after that, you will have to take a moment at any one particular support. So you take a moment at A. So if you take moment at A, so from here 10 into 10 is 100, which will act exactly at midspan, that is 5 meters from A. So 100 into 5, that is 500 kilonewton meter. Okay. And then 20 into distance is 15 meter. You take the moment. And then 30 into overall distance is 10 plus 5 plus 5 plus 5. Totally 25 meter. You take respectively. And then RB is acting towards up. So from here, distance is 20 meter, RB into 20. So all these downward forces are trying to hog the beam with respect to A, and RB is trying to sag the beam with respect to A. So that these are all negative, this is positive, you can consider, so that you will get the value of RB here, it is 77.5, and then RA plus RB is 150. So you will get RA equal to 150 minus 77.5 as 72.5 kilometers. So this is how to calculate RA and RB support reactions. So if you calculate RA and RB, it is easy to draw shear force diagram. And start from one end over here. Okay, or you can start from here also. So if we consider from this side, so from the section, consider section. If the force is at the right side, it is towards down, means it is positive. Our sign convention we define initially. So that 30 kilonewton you go up, and then till B there is no force. So same shear force it is subjected to. And RB value is 77.3. It is towards up, means it will be negative in direction. So 30 minus 77.5 you will get 47.5. So from here again till 20 kilonewton there is no load, same shear force, and 20 kilonewton towards down, so that positive 47.5 minus 20 you will get 27.5. So from here to E it is constant, and from here to A it is towards down, so that it will go to positive direction. And then as this is UDL in nature, UDL force, the variation of shear force will be linear. So 27.5 you deduct with 10 into 10, that is 100. 100 minus 27.5, you will get 72.5. So from here, the value of RA towards up, so that you, okay. So this is how to draw shear force diagram. So if you have any doubts in drawing shear force diagram, please ask me now. In this diagram, if you have any doubts about any value and sign convention. No doubts? Any doubts, Ilvendrappa?
ಇಲ್ಲ ಸರ್.
Yeah. And then you come for bending moment diagram. So bending moment diagram, at each section will calculate the bending moment. Bending moment at E, we have started with. So bending moment at A is 0. On what basis we have set the bending moment at A equal to 0? Here, the type of support, it is simple support. So obviously, here 0 will be the bending moment. At B, even though it is simple support, here moment will be there because there is a continuous span, overhanging portion is there. So moment at A, it is 0, and we can start with this point. Moment at C, because it is a free end, it is a 0 moment. So from here, if you take moment about B, from 30 into 5, that is 15. Okay, 15 is the moment about B due to 30 kilometers. So MB you can take moment at E. So moment at E, if you take 72.5 into 10 meters, so 72.5 is RA value. RA into distance is 10 meter from E to A. And then UDL, it is acting towards down, which is trying to hog the beam, 10 into 10, and distance is 10 by 2. So 10 by 2 is 5 meters. 22.5 is RA. So moment at E we are calculating. Any one particular side we should take. So RA is 72.5 into 10, and UDL towards down, 10 into 10 into 10 by 2. About E we take. So how much is the value of ME? ME value is plus 225 kilonewton meter. And the variation of this 225 kilonewton from A to E, it is parabolic in nature because UDL is acting over there. And bending moment at D. So from same side we are calculating 72.5 into 15. It is trying to sag the beam positive, and 10 into 10 is the UDL, converted UDL, into distance is 5 plus 10 by 2 is the distance. Okay, there is no other loads in between, so that is 87.5. And then bending moment at B. So same RA into 20, distance varies, and then 10 into 10 into half of the 10 meter plus 10 meter. And then there is another point load, 20 kilonewton towards down into 5. So 150 kilonewton meter, you are going to get the moment at B. And moment at C, from the same side, extra thing is distance varies. And then another reaction, 77.5, that is RB into 5 also will come. So moment at different control points we have calculated, that is 225, 87.5, 150, that is negative. Okay, all these things we have calculated. The moment at C we got 0 as it is free end. Okay, how to draw this bending moment diagram? As we seen here, at the point C it is 0, at point A it is 0. So at a point E, we calculated that is 225. So from A to E, parabolic variation you show it, and from E to D, there is linear variation as there is no load. Okay. So and then at B, we have calculated, so that is minus 150 you reach. While reaching at D, we should show 87.5 variation from 225. Okay, from here it is 0, it is already calculated. We just join. So this particular portion is subjected to hugging moment, and this particular portion is subjected to tagging moment. Okay. So you compare whether hogging is greater or sagging is greater. If you compare, tagging is greater over here. That is 225. So this particular portion of the beam can be designed for maximum 270, 262. So actually maximum moment will be there at point of like where the shear force changes its direction. So that particular location also can be calculated by using a similar triangle concept. That also it is shown over here. The point of counterflexion. It is one simple problem on shear force and bending. In the same manner, with the different loading conditions, you can go for solving the problems with different support conditions also. Yeah. Next topic. It is a simple bending theory, flexural stresses, and shear stresses. So for this, some introduction part for flexural and shear stresses. There is no problem with connection, right? Bending and shear stresses. Some introduction part. So beams are subjected to bending moment and shear forces, which vary from section to section. So to resist this bending moment and shearing force, beam section develops stresses. The stresses produced at any section to resist the bending moment is known as bending stresses. Okay. So sagging and hogging moment, it is shown like that. Some assumptions made in a simple bending theory you need to understand first. You can expect one single mark question from these assumptions. It is a simple bending theory. So beam which is initially straight and every layer of it is free to expand and contract. Okay. So initially which is rest, in each layer of this beam, it is free to expand and contract. The material is homogeneous and isotropic, same material for the dimension of beam it is used, that is the meaning. And Young's modulus is also same in the tension as well as compression. There is no change in value of E under compression or tension. And the stresses are within elastic limit. Plane section remains plane even after bending. And radius of curvature is large when we compare to the. So totally 6 assumptions are made in the analysis in simple bending theory. So among these, assumption number 5 is known as Bernoulli's assumption. So what this Bernoulli's assumption says is, so plane section, if you take some section AB, okay, it is shown here. So So there is a section AB over here. So this plane section remains plane even after bending, as shown in this A dash B dash. So there is no change. It remains. So this assumption is perfectly valid in case of pure. Okay, but shear also is associated with bending. Shear deformation distort the plane, and hence A dash B dash will not be plane in actual scenario. But we have to assume over here it is plane. Okay, and another assumption number 6, radius of curvature is large when it is compared to depth of the sea. So this assumption is also valid up to 1/10 to 1/5 of the depth of sea. When the deflection is less than 1/10 to 1/5 of the depth of sea. So until that only, this assumption is also valid. And then for solving problems in this chapter, for calculation of bending stresses, you must be aware of this formula. Derivation is there. You will have to remember this formula. M by I equal to sigma by Y equal to E by R. So this is very important formula in this chapter. M by I equal to F by Y equal sigma by Y equal to E by R, where M is the bending moment, I is the moment of inertia about the central axis. So sigma B is the bending stress, so Y is the distance of a fiber from neutral axis. E is the Young's modulus and R is the radius of curvature. Okay, so by using this formula, we can solve the problems. So let us see how to solve the problems by using this formula. M by I equal to sigma by Y equal to E by R. So one simple problem, it is one. A steel plate of width 120 mm and of thickness 20 mm is bent into a circular arc radius 10 meter. So here we have to determine the maximum stress induced and the bending moment. Okay, bending moment we should determine, and maximum stress induced, which will produce a maximum stress. Take value of modulus of elasticity as 2 into 10 raised to 5 Newton per meter square. So here the given data it is listed. Width B equal to width of the plate 120 mm is given here. Thickness of the plate is 120 mm. And then for the calculation we need a moment of inertia also. So moment of inertia of a rectangular section, that is BDQ by 12. In place of D it is T we are using. BT cube by 12, where B is 120, T is 22 divided by 12. And radius of curvature is 10 meter, it is 1. E value. Okay. From previous discussion, M by I is equal to sigma by Y is equal to E by R. We know the constants are proportional. So in that sigma by Y equal to E by R we have taken, where sigma is the bending stress, Y is the distance between the neutral axis and to the extreme. So value of E is there, that is 2 into 10 raised to 5. And then value of Y and value of R we should know. Value of R also it is there, 10 into 10 raised to 3 mm it is given. So bending moment we have to calculate, maximum stress induced we have to calculate. So in that value of Y, that is in place of D we substituted T, no? So that T centroidal axis if we take for 20 mm, exactly at 10 mm from top or bottom it will come neutral axis. From there extreme fiber distance is 10 mm. So for Y at 10 mm we can substitute E by R into Y max. So you will get a maximum stress 200 Newton per mm square. And then bending moment also we will have to calculate. M by is equal to E by R expression we are using. So this is why the reason why we calculated moment of inertia BTQ by curve here. We can substitute in place of I. E value, R value it is given. So that value of moment 1.6 km. So we answered for question, that is a bending moment which will produce the maximum stress. and also maximum stress also we calculated, that is 200 square. So simple expression, by using this simple expression, you can calculate the bending stress as well as bending moment. And then another problem, right over here, this is an hollow section. The external diameter is 140 mm and internal diameter is 120 mm. So here we have to calculate the maximum stress induced in this cast iron pipe, and the length of this cast iron pipe is 4 meter. So this pipe is kept on simple supports, and this will be carrying 80 Newton force at its. So when it is simply supported and span is 4 meter and point load 80 Newton is acting at mid span, we know how to calculate the bending moment with respect to this bending midpoint. It is WL by 4, where W is 80 Newton. So by using that formula, moment you can calculate. So external dia, internal dia, and length, it is listed over here. Maximum bending moment WL by 4, we get 8 into 10 raised to 4 Newton. And then for using M by I equal to sigma by Y, I value we need to calculate. So external diameter capital D, internal diameter small d. Pi d square by 4 is the pi d raised to 4 by 64 is the moment of inertia of a circular lamina, but it is not full area not to be considered here because it is an hollow section. Pi d raised to capital D raised to 4 minus small d raised to 4 by 64. So substitute for capital D and small d, we get moment of inertia of that 20 mm thickness as 1,17,809.7. So substitute the value of M, substitute the value of I, and the value of Y is capital D by 2, that is 20 mm. That is from neutral axis to extreme height of the distance we have taken, so that we get sigma value. So here we got sigma value 13.58. So this is how to calculate bending stresses in hollow sections. And section modulus in place of I by Y, wherever it comes, we can go for using a section modulus. Okay, that relationship you know. And M by A is equal to sigma by Y. So in sigma by Y, if you cross multiply, M will be equal to sigma max into I by Y. In place of this I by Y, you can write M equal to sigma max into Z. So that is section modulus. So moment carrying capacity will increase as the section modulus of the geometry increases. So moment carrying capacity of a section can be calculated like this, M equal to sigma max by that. So for standard geometries, for a rectangular lamina, you can arrive a section modulus formula. I is BD cube by 12, Y is D by 2 from this neutral axis. So that equal to I by Y. You substitute BD cube by 12 and D by 2. You are going to get that section modulus as BD square by 6. This is the standard formula you can use. If you do not remember also, like I and Y, if you know, you can calculate I by Y section modulus. And for an hollow rectangular lamina, the derived formula is 1 divided by 60 into BD cube by 12, capital BD and small bd. Okay. And in the same manner for circular section, pi d raised to cube divided by 32 for a circular section, normal circular section. If it is hollow in nature, pi d raised to 4 by 32 times of. So let us try to solve some problems here for finding the bending stresses. There is a cantilever beam of length 2 meter, and this beam will fail when the load is 2 kN is applied. Okay. At the free end, if the section of the beam is 40 by 60 mm, you have to find the stress at failure. Okay, for this you can calculate the moment. So with respect to this fixed support, if we calculate, moment is 2 kN into 2 meter. It is 4 kN meter. then length is 2 into 10 raised to 3, that is 2000 mm, and W is 2000 Newton already given, and cross section of beam also it is given. So for this we have formula M by I is equal to F by Y. So that is shortened with this formula M equal to sigma max into Z, where the value of section modulus Z equal to BD square by 6 we know. Substitute for the cross section elements, 24,000 mmQ section modulus you are going to get. So with this section modulus, moment also we can calculate, that is 2 kilonewton into 2 meters. You will get 4 into 10 raised to 3 Newton mm. So substitute over here, you will get maximum ending stress 166.67 Newton per. So this is how to calculate bending stress of a cantilever. And in place of a cantilever beam, it is placed simply supported beam here. But one different thing over here, it is asked to calculate what is the intensity of load, that is W. Okay. Again here bending moment you will calculate the maximum bending moment. Okay. So after calculating maximum bending moment, section modulus from given properties B and D geometries, we can calculate BD square by 6. And then WL square by 8 is the maximum bending moment formula. W is unknown, we keep it. Then the same formula which we used previously, M equal to sigma max to Z. So Z, it is clear value, it is there, and sigma max value is there. In place of M, that is 8,000 W Newton mm. So W equal to sigma max W by 8,000. We get 30 kilonewton per meter, the maximum intensity of load this beam can take. Okay, you can read what uniformly distributed load per meter of the beam may carry if the bending stress not to exceed 120 Newton per mm square. So not to exceed 120 Newton per mm square means in place of sigma we have substituted what? Okay. Then similar types of problems are there to calculate the bending stresses with other geometries like phase section or there is a symmetric phase section, non-geometric. But how to calculate a bending stresses in unsymmetrical section? Okay, for symmetrical section, we know where exactly neutral axis is there, and from that neutral axis, where exactly the extreme fibers are located, so that Y value easily we can take. And also, for calculation of a moment of inertia, also it is not a big problem. But when it comes to unsymmetrical section, you have to locate the centroid first, and then you will have to calculate the moment of inertia about the neutral axis or the required. So where lengthy calculation will happen in case of unsymmetrical section. So you see there is an unsymmetrical I section they have given one problem. Before that problem, introduction part you can see. In case of symmetrical section, neutral axis passes through the geometrical center of the section. But in case of unsymmetrical section like L and T section, neutral axis does not pass through the geometrical center of the section. Hence the value of Y for the topmost layer or bottommost layer of the section from the neutral axis will not be the same. For finding the bending stresses in the beam, the bigger value of Y is used as the neutral axis passes through the center of gravity of the section. Hence in unsymmetrical section, first we have to locate the center of gravity and then we have to start the problems. First problem on this, a cast iron bracket subjected to a bending has a cross section of the form with unequal flanges. Okay. The dimensions of the section are shown in figure. Figure is here. This is unsymmetrical I section. Top flange is 200 mm width. Bottom flange is 130 mm width. This is the bracket. Find the position of the neutral axis. That is first question. Moment of inertia of the section about neutral axis. Second question. If the maximum bending moment on the section is 40 meganewton mm, determine the maximum bending stress. That is third question. Okay, and also what is the nature of stress? Totally 4 questions are associated with this. We have to find the location of neutral axis. We have to find the moment of inertia of the section, and we have to find the maximum bending moment, and we have to find the bending stress, and also we have to determine the nature of stress. Totally 5 questions are associated with this question. This is the bracket. This is the section. 200, 130, 50, 50, 52. Okay. So for calculation of centroid, locating the centroid, you can divide this into 3 rectangles. 1, 2, 3. So you know how to locate the centroid. Y bar equal to A1 Y1 plus A2 Y2 A3 Y3 divided by A1 plus A2 plus A3. So this is the mathematical expression for locating the center of gravity for the plane sections. So moment of first moment of area normally we take over here. Distance is Y1, area is A1. Like that for other geometries also we have taken. So bottom flange area, that is first area we have taken bottom flange. 130 is the width, the height is 50 mm, area is 2500, and distance of CG from bottom. Okay, from bottom if we see, so it is 50 by 2. Somewhere here, its own centroid, it is line. So 50 by 2. And from the bottom only, we locate a centroid of each individual laminas from the base. Second area, it is 200 is the height and 50 is the width. So 10,000 mm square we get web area. And then distance of CG of A2. So 50 is the bottom flange height plus 200 is the web height divided by 2, that is 150 mm, is the total height of CG of A2 from the base. And third area, that is top flange, 200 is the width and 50 is the height. So 10,000 mm square is the total area. And then centroidal distance from the bottom base. So 50 is the bottom flange height, 200 is the web height, and 50 by 2 is the top flange mid height. Totally 275 mm is the height from base to CG of A3. So Y bar equal to A1 Y1 plus A2 Y2 plus A3 Y3 divided by A1 plus A2 plus A3. You substitute all these values in this formula so that you will get centroid of overall I section as 166.51 from bottom of the I. Okay. So if you want to locate the same with respect to top means, you deduct this 166.51 by overall height, so that some top line of the I section will get that value. Now you come for moment of inertia. So moment of inertia of each individual rectangular section we calculate and add it up here. And with respect to this in neutral axis, if we are locating by using parallel axis theorem, we can find moment of inertia of individual sections. So I1 is the moment of inertia of bottom flange about neutral axis. PDQ by 12 is the moment of inertia of rectangular section plus A into distance between a CG of individual bottom flange, CG, and neutral axis. So 166 is the total height from neutral axis to bottom base, minus 25 mm is the height from bottom base to centroid CG of bottom flange, whole square, A into Y bar square. If you do so, you will get this value. It is moment of inertia of this bottom flange. The same manner for web, first another top flange, calculate. So I2 and I3 you will get. So after getting I2, I3, overall I value is I1 plus I2 plus I3 we calculate. So now the top fiber and bottom fiber distance from 66.51 and 133.49 are the values of neutral axis distance from extreme fibers. Among this, so bottom fiber, it is 166.51 is the higher value. So 166.51. So that value we are going to use for the calculation. M by A is equal to sigma by Y, sigma equal to M by A into Y, where moment value already we calculated, that is WL square by 8, so 40 into 10 raised to 6 divided by I value just now we calculated here into 166.51. that is the bending stress we are going to get. That is 23.377 Newton per mm square is the maximum bending stress. So in the same manner for T section, so here unsymmetrical high section we saw. So same type of problem to determine the maximum tensile and compressive stresses. So in this T section, first of all, you need to locate the neutral axis and you will have to calculate the moment of inertia. Then by using the relationship m by is equal to sigma by y is equal to E by R, all these remaining tensile stresses and compressive stresses can be determined. As well as here, as the span is given and the load intensity is given, you can calculate the moment also. Length of this section, so same formula m equal to sigma z. As the section modulus increases, the strength of the section increases. And then shear stresses in beams. So till now, whatever we discussed, that is bending stresses. So shear stresses also we have to determine. So in previous chapter, we are dealing with bending stresses. And when we are dealing with bending stresses, like a pure bending case, shear force is 0. So shear stress in such cases, it is 0. Practically, this will not happen. Always there will be shear stresses also due to bending. At different section, there will be some certain shear force. As it is magnitude is less, we ignore it, we make it shear stresses are 0. But in actual practice, a beam is subjected to bending moment, which varies from section to section. Also, shear force acting on the beam is not 0. It also varies from section to section. So this is the formula we use for the calculation of shear stresses. Tau is a shear stress equal to F into A y bar divided by I into B. F is the shear force. A is the area of the section which we considered, about which we are calculating the shear stress. And then y is the distance between center of gravity of the area from the neutral axis. It is the shaded portion of area which we consider. And then I is the moment of inertia of the section. That overall areas of moment of inertia we are going to calculate here. B is the width of the section about which we are calculating the shear stress. So one simple problem for a calculation of shear stress. There is one rectangular lamina wooden beam, 100 mm wide and 150 mm deep, which is simply supported over a span of 4 meters. So the shear force at the section is 4,500 Newton. Find the shear stress at a distance of 25 mm above the neutral axis. So that is the question. A minute. At what time we started? Jay Surya? Jay Surya, are you there? Jamuna?
Sir?
ಎಷ್ಟು ಗಂಟೆಗೆ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ್ದಮ್ಮ at what time we started actually?
Sir, 5:35, 5:40, I guess, sir.
5:35, 5:40.
Sir.
Okay, fine. 20 more minutes. Yes, sir. Yep. So you see this rectangular lamina, wooden rectangular lamina. So here 25 mm above the neutral axis, we will have to determine the shear stress. So overall height is 150 mm. From neutral axis, 75 mm is the remaining height, as this is a rectangular lamina. So from here, 25 mm above means remaining is 50. 75 minus 25 is 50 mm. CG of this shaded portion lies at a height of 25 mm from this line. Okay, so shear force, it is given 4,500 Newton, and then this moment of inertia I, that is BDQ by 2 with respect to reference axis, we can calculate. And value of width P is 100 mm, as it is not varying, same width throughout the section. And then value of A and value of Y. The value of A is the area of the beam above Y1. That means this only shaded portion area. So what is the area of the shaded portion? 100 mm is the width and 50 mm is the height. So that 5000 mm square is the area, and y bar is the distance between neutral axis and CG of the shaded portion. So what is this height, overall height from the CG to neutral axis? Jamuna?
So 50 mm.
It is 50 mm because 25 mm from here to here, and from here to here again 25 mm. So total it is 50 mm. So all the data which are required in this formula, we got it. We just need to substitute. That is 4500, and 5000 is the area, 50 mm is the y bar, and BDQ by 12, that is this value is I value, and then I into P. P is 100. So 0.4 Newton per mm square is the shear stress at an height of 25 mm from the neutral axis. So here they have mentioned 25 mm. It can be asked some other value also. Same procedure you can go for using. So mandatorily you should remember this formula for shear stress. That is tau equal to F into A into y bar divided by I into. So any cross section you get, you can use the same formula. You can get the shear stress. So you can go for solving the problem for a triangular section over here. So in this triangular section, there is a beam of cross section isosceles triangle. The two sides are same, subject to a shear force of 30 kN at a section where base width is 150. So this base width is 150 mm. Total height it is 450 mm. So we'll have to determine the horizontal shear stress at neutral axis. So neutral axis lies at a height of 1/3 of height from base or 2/3 of depth from apex. So 1/3 of 450 if we calculate is 150 mm from here. So this is the neutral axis. You will have to determine horizontal shear stress at neutral axis. The distance from top of beam where shear stress is maximum. So from point B, where exactly the maximum shear stress is acting. So that height also you will have to calculate, and value of maximum shear stress also you will have to calculate. Okay. So first you take the given data, that is 30 kN nothing but 30,000 Newton, and base width is 150 mm, height is 450 mm. To calculate the horizontal shear stress neutral axis, the neutral axis for the triangle lies at a distance of 1/3 of height. So 1/3 of height you calculate, that is 150 mm. 2/3 of height you calculate 300 mm from the apex. So now the width of a section at the neutral axis. So what is the width over here? This width that is given in the question, that is 150 mm. But neutral axis at an height of 150 mm from the bottom. What is the width over here? So where exactly the shaded portion area need to be considered for calculation of shear stress. So value of NA by using the similar triangle CD and DNA. So you can take CD divided by NA equal to 450 divided by 300. However, value of CD you know, that value of CD is 150, so that you will get value of NA. So CD is 150, 150 into 300 divided by 450, you will get value of NA as 100 mm. So you use this formula tau equal to F into A y bar divided by into P. So here the value of we know, and the area is above the axis at which shear stress is to be find out. So over here the area half into base is NA and height is 300. Height is 300. So and y bar distance, that is the distance of CG and neutral axis. So that is, so from here the CG is located at a height of 1/3 of 300 mm. 1/3 of 300 mm is 100 mm is the value of y bar. So I is PH2 by 36 in case of triangle. So H value you know. So overall moment of inertia you should take for the figure. 150 is the base width, height is 450, PH2 by 36, you will get the value. So F is 30,000 and A is 15,000. That is you just calculated the overall area of shaded portion, and then 100 is the y bar value. I value is the BH2 by 36, into width, the 10 what you calculated, that is also 100 mm. So if you substitute all these values, you will get the shear stress as 1.185 Newton per mm square. So this is the shear stress at neutral axis. We just answered for first question, that is horizontal shear stress at neutral axis. But now two more questions are there, that is the distance from the top of the beam where shear stress is. So from here, where exactly the shear stress is there, and then its value also we have to calculate. For that, let us consider another section, that is EF, at a distance of x from apex, where exactly the maximum shear stress is experiencing. So if we take only this BEF as the shaded portion, this particular area centroid will lies at a distance of 1/3 of this x from the bottom, or 2/3 of x from the top. So for this, we have to take y from the neutral axis. So the distance from the top of the beam where shear stress is maximum, that we are trying to find out by using similar triangle concept. EF divided by CD equal to x divided by 450. So BEF and BCD, similar triangle concept we are using, so that we can express this base width EF in terms of x, that is the height at which the shear stress is maximum. So x divided by 450 into CD is 150, so that EF equal to x by 3 we will get. And we have the formula tau equal to F into AY per divided by AB. So in this, let us try to substitute. Area is this particular area we should consider, that is BEF. So that is half into base into height. So half into base is EF. EF is nothing but x by 3, and height is x. So x into x by 3 into 3 into 2, 11. So that you will get x squared divided by 6 is the area of BEF. And then the distance from the neutral axis to centroid of this BEF is 2h by 3. From B, the neutral axis is located at. If you deduct that with 2x by 3, you will get distance from here to neutral axis. So if you substitute the h value as 450, in terms of x, you will get 300 minus 2x by 3 as the distance of CG to the neutral axis. So this is the y bar distance. We will moment of inertia of a BCD about a neutral axis. So BCD overall area we should take. So finally you substitute for tau, F is the shear force 3000, and then area we need to consider only BEF, that is x squared by 6, that is written over here, and then y bar value is 300 minus 2x. So that is what you calculated here, and then value of moment of inertia I, that is bs2 by 36, and then width is EF as x by. So finally you will get the shear stress as 0.000395 into 300x minus 2x square by 6. So here we have to calculate the value of x. For the maximum shear stress, we will have to differentiate this tau equation with respect to x and equate it to 0. So if you send this value this side, this will become 0. So that 300x minus 2x cubed, 2x square by 3, we just need to differentiate it. If you differentiate it, you will get 300 minus 4x by 3. So that value of x we are going to get as 2.5 mm. So in the same equation, this one, if you substitute the value of x as 2.5, you are going to get the maximum shear stress as 1.333 Newton per meter square. So maximum shear stress we calculated, and location at which the maximum shear stress is acting in this triangular lamina. So some of the standard cases like rectangular lamina, how the shear stress distribution varies. So some standardized formulas are taken, and only for rectangular section and a circular section, we have certain specific formulas which are derived. So in case of rectangular lamina, we can relate maximum shear stress with average shear stress. We can see one simple problem here. There is a rectangular beam of 100 mm width and 250 mm depth, which is subjected to a maximum shear force of 50 kN. Here you determine average shear stress, maximum shear stress, and shear stress at a distance of 25 mm above the neutral axis. So average shear stress means here we are going to take whole area and full shear force which is acting. We just need to divide load by area. So this area is 100 into 250 mm, so that 50,000 divided by BD you get 2 Newton per mm square. But this average shear stress is not equal to maximum shear stress. It is always less than maximum shear stress. So maximum shear stress will act at neutral axis line. So there is a relationship between average shear stress and maximum shear stress. Tau max will be equal to 1.5 times of tau average. So this relationship you remember, this is applicable only for rectangular section. Tau max equal to 1.5 times of tau average. So multiply with 1.5, you will get maximum shear stress. And shear stress at a distance of 25 mm from the neutral axis if it is asked. Same manner we have solved one problem also. But here also for only for rectangular section there is a derived formula you can remember. Tau equal to f by 2I into d square by 4 minus y square. If you do not remember this formula, you can go for using the same formula which we used initially, that is f into y divided by I into that first formula we used, that is f into a y bar divided by I into t. This shear stress formula you can use and you can get 2.88 Newton per meter square. For circular section also there is a standard formula. So tau max is related with the average shear stress. So that is multiplied with 4 divided by 3. So tau max equal to 4 by 3. So average shear stress you can calculate by dividing the area the given shear force. You just multiply with 4 by 3, you will get maximum shear stress. This is the example formula. And then shear stress at a distance of 40 mm it is asked. This is exclusively for circular laminas. Tau equal to f by 3I into r square minus y square you can use, or else you can, in place of this, f into a y bar divided by I into t, that formula you can use. So for symmetrical section shear stress, there is also one more standard formula for calculation of maximum shear stress. This formula you can use. Next topic, it is columns and struts. So failure of columns and then buckling topic we are going to discuss this. This we will discuss in next session. So next week we can go for discussing about this. Just a minute, we will. Yeah. So with respect to shear stress, any doubts? Jayasuriya, Chandana, Jamuna, Janardhan Chari.
No, sir.
How about Chandana and Jamuna?
No, sir.
You do not want to talk?
No, sir.
Okay. Okay, fine. So let us see the syllabus, how much topic we covered today. So that is in structural engineering, solid mechanics, bending moment and shear force we saw today for statically determinate structure, simple stress and strain relationship we saw, simple bending theory, flexural and shear stresses we saw. So I was about to cover this topic, buckling of column. So we are going out of time. So let us see some topics: uniform torsion, shears, and transformation of stresses and buckling of column in next session. Yeah. So I will stop here. So let us meet in next week. Okay. Yeah, fine. I hope we started at 5:40. Jamuna, Surya.
Yes, sir.
Fine. I'll stop now. Yeah. See you. Thank you. Bye.
Thank you, sir.